Good morning. I will give my presentation about the practice of Cloud Native NFV infrastructure networking on ARM. What our agenda is, first one is what is Cloud Native? And for the Cloud Native networking, I will give out the containerized NFV infrastructure networking on ARM and the container networking solutions comparison on ARM and Cloud Native network microservices and our next steps. So what is Cloud Native? Cloud Native is an approach to building and running applications that exploit the advantages of a cloud computing delivery model. And there is a community named Cloud Native Computing Foundation, CNCF. CF's definition of CNCF is that for Cloud Native, we typically use open source software stack to be containerized, where each part of the application is packaged in its own container and dynamically orchestrated. So each part is actively scheduled and managed to optimize resource utilization. And for Cloud Native, we are use the microservice oriented to increase the overall agility and the maintainability of applications. And nowadays, Kubernetes is a popular container orchestration platform and the first CNCF authorized projects and CNCF authenticated project. Kubernetes helps users build, scale, and manage their applications in a dynamic way and for their whole life cycles. So high-performance networking is the key of containerized Cloud Native infrastructure for microservice architecture. So we've talked about the containerized NFV infrastructure networking on ARM. For the Kubernetes networking model, we have 3 requirements. The first one is that all ports can communicate with each other with other ports without using network address translation, which means we use the same flat networking address space. And all nodes can communicate with all ports without NAT. And the IP that a port sees itself is the same IP that others see it. So all the networking name address space is flat. The networking objects in the Kubernetes are the container-to-container networking, port-to-port networking, and port-to-service networking, and the internet-to-service networking, which is almost the same for the Cloud Native environment. Container networking solutions like Flannel, Calico, Viv use a VETH with a bridge, a router, and some overlay routing manipulations to do the networking. And here is a list of the Kubernetes supported container networking solutions, such as Flannel, Calico, and Contiv, and Cilian, and Martas, and host network, and all things like that. Here, the Martas is not truly really a container networking solution, but a solution for to integrate multiple container networking solutions to support multiple interfaces, to provide multiple interfaces to a single pod. And in this presentation, I would like to give a little introduction to Contiv VPP, which is a VPP-based container networking solutions, and the project Calico, which is widely used these days, and which is high performance and with easy deployment. And OVN-Kubernetes, OVN-Kubernetes is a container networking solution which uses OVS to do the container networking and uses OVN controller to do the deployment. The first one is Contiv VPP, which is a high-performance container networking based on the FAT VPP. We know that FAT VPP is a vector packet processing to provide network connectivity between the pods in a Kubernetes cluster. And it deploys itself as a set of pods in the kubesystem namespace. And some of the components are Contiv KSR, Contiv etcd on the master node. Contiv KSR is used to monitor the Kubernetes behavior to do the deployment to Contiv VPP, and the Contiv etcd to store all the needed configuration for itself. And for the data plane, we have the Contiv vSwitch. Contiv vSwitch contains the VPP vSwitch in the container, and there has a Contiv VPP agent to do the deployment, to do the configuration for the VPP, and get the configuration from the Contiv CNI. And the Contiv CNI is used to get the configuration information from the Kubernetes. For Contiv VPP, which can support the network policy using the VPP's internal traffic mechanism, such as ACL, load balancing, and NAT44. And for Contiv VPP, we use the DPDK as the main networking interfaces to communicate all the ports across hosts. This graph gives a typical deployment for that on the ARM server, and we have Kubernetes to do get the configuration and to communicate with Contiv CNI, and the VPP agent is used to get the configuration and to do the configuration to VPP plugins. And for the data plane, on the data plane, the VPP vSwitch do the actual packet switching between the containers. And we have done some things on the Contiv VPP on ARM. We have enabled a Contiv VPP on ARM platform and added ARM 64 building and utility scripts for Contiv VPP Docker images building and management. And we added the corresponding Kubernetes setup template file regions to make file to enable config file generation for ARM. Added the manual installation guide for ARM. And we have done the container networking verification with Contiv VPP on ARM servers. This is a simple test for the ping round trip time. With you use the OVN-NFV yardstick, and on the this is for the ping RTT for the between two hosts. For the upper level, we use Fnano. Fnano is a very popular container network solutions, but with an overlay solution between hosts. So it has very large delay, very large ping RTT time, which is in seconds level. But for Contiv VPP, the communication between pods in two hosts is via the DPDK, and so the ping RTT time is greatly shorted in a microseconds level. And for Fnano, which is a native overlay solution, but for Contiv VPP is a direct DPDK-based solutions. Another available network container network solution is Project Calico. Calico is very widely used today, which has many desired features, such as it's a network layer solution which uses routable IP addresses for containers to the rest of the world. Hence, parts are concurrently exposed to the outside world, no encapsulation needed. So it's a has a direct route table in every host to direct the packet routing for the containers. And Calico can support Kubernetes network policy very well with the IP table supported inherently. So we have verified the Calico project, Calico on ARM. And actually, these days, we have deployed Calico in our some of our edge computing and cloud computing projects, such as IEC in Ukraine, with our this is a deployment file for the Kubernetes, which is think to be very easy and simple and direct. And the richest deployment is the same as that in the x86, and with just many three ports in the Kubi system namespace. From the version 3.2, the ARM64 platform has been supported. We have put some patches to the Calico community to add support for ARM. And most of the scenarios have been verified on ARM64, such as port-to-port communication, node-to-port communication, Kubernetes network policy, Layer 3 networking policy, and IP-IP tunnel. All the main components, such as Calico node, Calico controller, Calico CNI, and Kubi controllers, and the Typher are verified on ARM platform. Another very important, the third very important container network solution is OVN-Kubernetes. We know that OVN provide open virtual networking provides network virtualization to containers. And OVN can create a logical network amongst the containers running on multiple hosts. It's composed of two databases, such as the northbound database and the southbound database. For Kubernetes, OVN provides the following things. First one is provide a logical switch created per Kubernetes node, and then interconnect all these logical switches with a single logical router. And any containers get connected to a logical switch as a logical port. And it adds an additional logical port for Kubernetes health checking. And it uses OVN gateway in the nodes to reach Kubernetes central daemons with NAT. The OVN architecture is very direct, which is composed of the northbound and southbound databases to store all the needed logical switch and the physical implementation of the switches. And the right down part of the graph is for the OVN Kubernetes networking abstraction to collecting all the containers. For OVN Kubernetes, the manual installation has been verified on ARM. So we have deployed OVN Kubernetes successfully with manual installation and with all the SSL certificates enabled. But OVA's DBDK in OVN Kubernetes is to be verified. We have done some initial tests, performance tests between the Calico and OVN Kubernetes. For this graph, it shows a port-to-port communication in the same node. It is tested by iProof 3, and we see that Calico achieves a little bit higher performance than the OVN Kubernetes, but the difference is very small. difference is very small. And the reason is that OVN-Kubernetes is based on the kernel data path module to do the forwarding. And for Calico, it is directed by the kernel, not by the not by the kernel module. And so the another performance factor is I think is ETH pair performance, which is a little bit higher than the OVS port. So we have think something about what is a good container networking solution. So we think that easy installation, maturity, and the feature reach and the scalability to be very important. And for the on the low level, we think it is for the lower networking support, such as we do the networking via the pure kernel or overlay incorporated or DPTK enabled. And for the easy installation, we think Kubernetes daemon set with YAML file installation is very simple, and the easy configuration and management, and the multi-platform support. And for the features, I think load balancing, network service, network policy, and network security are all supported, are all very important. And for scalability, and I think it should support a large number of Kubernetes nodes and Kubernetes ports. This table gives a initial comparison for the features. All the solutions, I think all the solutions are supported on ARM nowadays. So we can use all these solutions in our Kubernetes networking on ARM. But if you want to choose a desired feature, a special feature you want to use, you can only be very selective on these solutions, because if you want easy installation, I suggest that you use Funano or Calico. But if you want to use very high performance, you can use Contiv VPP. All these solutions have its own limitations and restrictions. So I would like to talk something about the Cloud Native microservices. The first microservice we have enabled on ARM is the Legato SFC controller. For the Legato SFC controllers, we know that when we have deployed several pods, we need to deploy a service function chain between these pods, which means that all the traffic between these pods and should be directed to another pod in a service function chain. And in this graph, it's a sample use cases with Contiv VPP. And we deployed the service function with memory interfaces with VPP, and collected the in this graph VNF1 and collected with VNF2 in a single service function chain, and the VNF3 with VNF4 in another service function chain, and then the service function chain is done via the VNF overlay tunnel, which is by a VXLAN tunnel. And the deployment is by a YAML file, and the service function chain controller is used to do the actual deployment. The second cloud native microservices is Envoy proxy. We know that Envoy is done the data plane proxy on the microservice, and in this simple samples, we use Nginx as a back-end web server. And from the front end, we use Envoy to do the proxy. And Envoy works in a sidecar model, And so on the control plane, there has 3 components. It's STL manager, mixer, ISO, auth. And Envoy uses a typical and rather standard protocol like standard protocol to do the communication between the control plane and the data plane. So for the Envoy, it is a standard implementation. And for the Envoy, it can do some other enhancement for the native web server to the native web server, such as rate limiting and authorization and do the certification and all things like that. So it is this Envoy example had been enabled on ARM. The third microservice example is for the network service mesh. For the network service mesh, we added the following properties to networking in Kubernetes. And first one is heterogeneous network solution configurations protocol, and on-demand dynamic negotiated collections, and the tunneling as a first-class citizen, and the networking context as a first-class citizen, and the policy-driven service function chain. And I think network service mesh is a novel approach solving complicated layer 2 and layer 3 use cases in Kubernetes, which maps the concept of a service mesh to layer 2 and layer 3 payloads. And as we know, if we have deployed the Kubernetes pod, we want to add some interfaces to this pod after we have spawned these pods, and to add some extra collections to these pods, such as we want to enable extra collection between these pods for the layer 2 or layer 3, such as add a VLAN to a single pod, to 2 pods, and another VLAN to another 2 pods. This can be done in Kubernetes via the network service mesh. So it's a very great enhancement to the original Kubernetes networking. For these services, originally we have the Marta's CNI2, but Marta's CNI is very static and not so scalable. So for the network service mesh, we can down it dynamically. For next steps, we are thinking about high-performance container network solution verification for the far edge devices, such as malware, Maxio, Bing, and some of the small boards. And in the future, we would like to enable something like the Kubernetes Edge or something like that. And for OVN-Kubernetes and the daemon set installation is not okay on ARM these days. So we would like to enable OVN-Kubernetes daemon set installation, which is an easy installation for that on ARM. And OVN-Kubernetes performs evaluation with OVS DBDK enabled on ARM, and with fewer cache pieces and TLB misses and context switches. And the network service mesh, for the network service mesh, we would do some enablement with Contiv VPP on ARM. And the container networking for edge computing projects we have in, such as Ocarina, we have proposed a project named IEC. And for IEC, we use the Calico as the main solutions. But we will do some modification and do some adaptation to these solutions to provide the lightweight networking solutions. And a comprehensive, we like to give a comprehensive container networking solution selection mechanism based on the different use cases of on ARM. So this is all my presentations today. Thank you all. Do you have any questions?
Yeah. So if you were trying to select a solution for small nodes, which networking solution would you go for?
Yes. For small nodes, such as these days, we are considering is that if we small nodes, so small nodes, we do have a very small number of CPU cores. If you do have a very small number of CPU cores, if you use Contiv VPP, it needs DPDK. And for Nano, it uses overlay solution. So if we want to use DPDK will occupy a number of CPU cores. So for the performance consideration, Contiv VPP is not very desired because we have very limited number of CPU cores. For Nano, it uses overlay solution, and the performance of this small node is very performance limited inherently. So Nano is also not desired. So after all this consideration, so we choose Calico. Which Calico is based directly on the kernel, and there is easy installation, easy kernel adaptation. So for the Calico transplantation, we still have to do some modification to the kernel configuration to enable the Calico desired requirements, such as we have to enable net filter and all things like that in a small kernel. We have to do the kernel adaptation. So this is a very all this consideration when we choose a proper solution for container networking on a small node. Yes, for the CPU cost, the memory, and for the performance restrictions such as overlay solutions. So, and another important selection criteria is for the easy installation. For Calico, such as Calico, we use a YAML file to do a simple YAML file to do the deployment. And when a new node is added, all the needed installation ports are added automatically, not manually. So all these criteria should be considered when you choose a proper solution on these nodes. Okay. Thank you all.